All right, so and now that last time we looked at complexity of GLMs, which are much more statistical. So remember, I started with example one, which was spin glass, because we're in the physics community, and because in fact this is what guided the thinking here. And the first works on complexity were done there. Then we went to Tensor PCA, which was a spherical spin glass, but equipped with one signal. And then we went to GLM, which looked like completely different. And I told you, in fact, in the end, okay, you have to resort to a completely different and more complicated model of random matrices to understand the complexity. But the way to do it is the same. To be honest, of course, to understand the complexity, the final problem I showed you, the variational problem of all possible GLMs is a hard task, even after our work. But the thing is the same. And I gave you this interesting thing that the true loss function of a GLM, a planted GLM, the one I called L2, in fact has the same kind of structure than Tensor PCA. Once you decompose this in this trick of Hermite polynomials, you had something very similar. It's a function of the latitude, and it's more complicated than a function of the latitude for the Tensor PCA, because in the Tensor PCA, this function was just the power of the latitude. Okay, and here is just a power series of the latitudes. All right, that's where we were. So now, back to the initial problem, we have this empirical risk, loss, energy function, whatever, which was written like this. And the data are IID, unstructured. You have, okay, sorry for that. Then as above, n in the dimension of the parameter x, which initially I called theta, so that was my sphere, d the dimension of the data, and m the size of the sample. Okay, our three examples above are of this type. Sorry for that. So remember that the spherical spin glass, Tensor PCA, and GLMs are of that type. Okay, we're exactly doing that. And so the question now, and also the P plus K model, which was a little academic model, but of the same type. So the question is, understand the performance of the simplest dynamics, the plain vanilla dynamics, to find the minimum, if possible, of this random function, which is the empirical loss and whatever. So I will say a few words, and I've already said, in fact, words about Langevin, gradient flow, gradient descent, stochastic gradient descent, online gradient descent. And as I say, I don't have much to say on the real hard stochastic gradient descent when you reuse and all that. This is coming later. So I will first start with our example one, which was the spherical spin glass, and I will first, because we're in a physics school, do a little survey of what has been known for a long time in physics on the Langevin dynamics for this thing. And maybe some of you already know that well, but in a few slides I will try to summarize decades of work, in fact. So the Langevin dynamics have been studied for decades, literally, since the 80s, for the case of spin glasses, as well, of course, as the Glauber dynamics if you take Ising spin. Here I'm talking about continuous spin, soft spins, but you could, of course, look also at Glauber dynamics. In this case, this question about complexity is meaningful easily on soft spins and much less on hard spins. But for dynamics, the question is really similar. So here I will concentrate on Langevin type dynamics, smooth dynamics, but results are known also for Glauber dynamics. Okay, so Langevin is of course something like this. H is here for Langevin dynamics, I write H because it's a Hamiltonian, but in fact it's the same as our empirical risk function, R hat. Okay, and then, so the mixing of these dynamics is typically exponentially long at low temperature in the glass phase. So if you want a mathematical proof of that, it has been done and a characterization and when it's true and when it's not true, it has been done in recent works by Reza Geysari in l'Institut Henri Poincaré in 2019, and myself and Jagannath in CMP in 17. So there you have something which is really differential geometric-like. That is, if I give you the H, the Hamiltonian, or R hat, whatever, and then you use the usual tools of isoperimetry, Chigger, whatever, to understand when. There are generic tools to understand when a spectral gap is very small, and so when the mixing time is very long. And there you have conditions for both Ising and continuous things to prove that the spectral gap was, that the mixing time is exponentially long. It was curious when I've been working on long-time dynamics of spin glasses since the 90s, but in fact, there was no proof of that anywhere. That's the simple fact. Okay, so, but it's of course no real understanding when is it true that the mixing time is exponentially long. Of course, for spherical spin glass, it is the case at low temperature. And, but not necessarily, not for every spherical spin glass, right? It's true, for instance, for the pure spherical spin glass, because in fact you have a 1 RSB phase at the bottom, right? So as soon as you want a 1 replica symmetric breaking phase, you have this terrible glassy landscape, which of course will create very slow mixing. But I don't give any guarantee on mixtures of spin glass. Okay. So in every, but we have a general theorem saying if this happened, then you have exponentially long time scale. In this, so you have an exponentially long time scale, which is the time for mixing. Like say exponential times 18 times n, okay? But now you could look at time scales which are exponential Cn, where C smaller than 18, right? Very long time scale, but not yet enough to get to equilibrium. So physicists call that usually, and I don't understand why, but you probably do, activated dynamics. I don't know what activates anything, but anyway. So, by the way, if somebody understands, please tell me. So in these very long time scales, very interesting things happen, which are very universal. And this is aging, and the aging in spin glasses is in fact very simple. It looks terrible, but it's the simplest possible aging there is. And and this is what I've been studying for 15 years. So, and of course, physicists had done that before me. Oops. Okay. So typically, oops, sorry for that really. So here's the lesson of 20 years over 15 years of aging. The configuration, of course, mathematically, these are very long things, but this is what it means. In this very long time scale, exponential Cn, in the good situation, like what the configuration does is it stays stuck in deep traps for exponentially long lengths of time, which are of the same order than the time it took to find the traps. This sentence is important. So if you are exponential Cn, time, in those time scale, you will find traps which are of depth d, usually in the usual normalization, d times n. This d depends on c. Okay, so in a given time scale, you will find traps at a given depth. They are hard to find. That's why it needs so much time. They are hard to find independently of the question of the other traps. They are hard to find just because of entropy. The traps are rare. They're hard to find. And at times, it's the problem of a needle in a haystack. If you want to find a small cloud in a very large space, it takes time. And so the time to find those traps of depths d times n is exponential Cn, and the d is calibrated so that the time to get out of them is also exponential dn. So if you look at this time scale, in fact, you visit plenty of other traps, which are shorter, less deep, but which, of course, in which you spend exponential C prime n time in them, and C prime being strictly smaller than C, in the time scale exponential Cn, it doesn't count. So the other short time, the other traps which are less deep are essentially not important. And you have the deeper traps, but these deeper traps are not important in these time scales because you cannot find them yet. Okay? So that's just the thing. And so if you just forget everything but the traps, the motion is just a very simple motion between the traps, right? Which has been, in fact, predicted by Bouchot a long time ago. And this motion is called, if you go into these papers, this has been known in math for a very long time. It's called fractional kinetics, and the aging follows the arc-sine law. Yeah?
So how can you find the more shallow traps and not find the deeper traps?
Because you have many more.
Many more shallow traps?
Of course. That's the story.
But if you visit, so you don't visit all the shallow traps?
You don't visit all, but you visit plenty of them. But still, it doesn't count. in the timescale exponential dn.
Aren't there exponentially more shallow traps?
Exponentially more, yeah, but you don't see them in one trajectory, okay? So this has been done mathematically first. So Bouchot introduced it in fact, a toy model on the complete graph in the 90s, and his intuition, on the complete graph, you can compute everything very naturally, and you would find this arcsine law, and he didn't describe it like this, but it's that. And then the mathematician, embarked in proving this, and we did that with Antoine Bouvier, Véronique Guérard, Jiří Černý, in different groups in the 2000s first for the random energy model, then for the Ising p-spin, for simple random hopping trap dynamics, or Bouchot dynamics. And more recently, Guérard and Černý have done that for the REM with the usual Glauber dynamics. In fact, it's not yet done for the spherical p-spin and the Langevin dynamics, really rigorously. And I've seen recently, it's clear that it will come, because now that we have the tool about in fact, the study of complexity was to do that initially. And then I was sidetracked. But I think this will be done probably, I'm almost certain that, I shouldn't say that, but that Giulio, Chiara, Valentina will be doing something like this. But anyway, the picture is expected to be true. Okay. Okay, Langevin dynamics for the spherical spin glass. Now the question is, all this is interesting, but that was what was interesting for physics, in fact, this activity thing, but the very long time scale, but absolutely not interesting for data science, right? You don't want to run an algorithm for exponential Cn. So I'm looking now at shorter time. In fact, much of the early physics literature considered the short time regime, which is to let n tend to infinity first, and then possibly the time tend to infinity. So you have to realize that the order of limits is crucial. If you let first n to infinity, it means that the time that you're looking at, right, are constant. You cannot have a time that diverges with n, right? In this limit. The other thing was, so in this limit, this was done a long time ago. For instance, you could look, this is how I started this thing in this chapter 5, I think, of Mézard, Parisi, Virasoro, where there's a little explanation of the form literature before that. Maybe Sampolinsky Zipelius was a very important paper in the 90s for Sherkin Kirkpatrick and the soft spin case. And more importantly for us here, Cugliandolo, Kurchan, and others in the 90s for the spherical spin glass case. Okay, so what appeared there, here. So this regime has also been studied in the math literature. That was a PhD thesis of Alice Guillonnet in the 90s with me, and then there was work, that was for the SK model, and for the spherical case, there was, we studied that with Amir Dembo in the aughts. There is a very recent work, in fact, a few weeks ago by Dembo, Lubetsky, and Zeytouni. You might not be interested in this direction, but they prove that the result that we have proved here with Alice and Amir are correct when the couplings are not Gaussian. So universality in the non, this looks like nothing, but it's a hell of a work. It's hard, really. But the end result is every result proved before is also correct there. Okay, so the important idea that introduced by the physicists, by Cugliandolo, Kurchan, and others, I'm sure I hope I don't offend anybody here, was to use two time functions, C of t and t plus s, is the correlation between the configuration of the system at time t and at t plus s. And R being the response function, I won't describe what that is. So this allowed, why did they do that? Because this allowed them to close, and when we followed their tracks, we did the same thing, to close the mean field dynamical equations. So when you look at this Langevin equation, you have n equation if your spin is size n, and okay, you look at the empirical measure of this thing, it's hard to close. It's hard, so for the SK case, for instance, we could close it, but it's an infinite dimensional thing, which is essentially impossible to study. So the nice thing in the spherical case is that Cugliandolo, Kurchan, and others managed to find an autonomous equation for these two quantities. Right? And physicists like to have equal signs, right? So an equation, you close, you have something, and then maybe you study it. In this case, then the next step was to study the long time behavior of these limiting Cugliandolo-Kurchan time equations. But this hit a wall. In fact, at the end of the 90s, beginning of the aughts, then all sorts of people got involved, you had supersymmetry thrown in and so on, but it hit a wall. The reason is that so you wanted to study aging in this short time regime. Right? So you wanted to say that C of t and t plus s converged to something when s was proportional to t. That's aging. S is the time. So you look at the configuration at time t, and at time t plus 3t, and you want to say something. Right? That's aging. The problem is that they could find what the aging equations should be, but there was an infamous problem, which is called the matching problem. And this matching problem is a fact that these limiting things are not well determined. You have a whole class of possible things, attractors, if you want, in the space of dynamics, which are invariant by time reparameterization. And you have nothing to fix this time reparameterization. So this kind of hit a wall, which obstructed the proof, at least mathematical proof of an aging regime. Okay? All right, so that was the state of things, you know, around 2000 or something like that. Okay. Then, but so here, we are still interested to try to do something for these landscapes. And of course, the first thing to try is the spherical spin glass. Okay, so we have a more recent approach with Reza, Geysari, of course, Jagannath. You've seen those names a lot, so maybe I should mention who they are. Reza is a student of was a student of Eyal Lubetsky at Courant, is now a postdoc at Berkeley. Okosh was a student of mine, is now a professor at Waterloo in Canada. So this is a paper in CMP of last year. And we come back to studying these equations, but now forgetting the physics approach of having two times, just doing the usual math thing, having one time. But when you have one time, you cannot close the equations. Okay? But still, you can do analysis. You can bound. So mathematicians are happy with inequalities. Okay? That's what we do here. So what we study, for instance, is the value of the energy, the Hamiltonian, the loss, if you want, at time t, and the norm of the gradient of the loss at time t. Okay, and that we can follow. This is based on a very heavy analytical technique in this paper that we call bounding flows, because we have to control an infinite hierarchy of equations instead of only one or two. But this is the price to pay for not closing the equation as in Cuglian-de-Locochan, but it can be done. The result is not as precise because it's not an inequality. It's a bound. But for instance, this allows us to prove the following. In finite time for Langevin, the system will end up, so you start from a random infinite temperature thing. The system will end up in a region where the energy is low, proportional to the ground state. Of course, above, for those who know above, the so-called dynamical threshold. And more importantly, where the norm of the gradient is bounded below. And then stay there. The system will stay there. That is low energy, so the system performs pretty well. Maybe you get 70% of the ground state. And the gradient, the norm of the gradient is large. So nobody cares about critical points. In this time scale, there's nothing like the system has to go to a critical point. Every time I hear this, I'm very suspicious. Right? In this case, the system does not even come close to a critical point. Okay? In infinite time, in this time scale, when you first let n go to infinity. So what, of course, what does it do? Well, how can you imagine in infinite dimension what is? If you do this, okay? So what this says, that this means during this descent phase, the system manages to go down deeply and ignores completely the critical points of all indices, saddle or local minima, even though they are exponentially numerous. You just don't see them. You just zoom. The system doesn't care about the complexity of the landscape. So the complexity plays no role in this phase. Okay? So this is the lesson of this paper. Okay, what's going on? So this paper was done in this paper, Bounding Flows. I don't know if I mentioned which appeared in 2019, I think, in CMP. And this has been pushed now, of course, this was just a testing ground. We didn't try to prove new things for spin glasses per se. We wanted to have a robust tool to study Tensor PCA or GLM and so on. So this has been pushed to PCA and to Langevin dynamics for PCA, and also for gradient flow, continuous time gradient descent, if you want. In this paper, algorithmic threshold for Tensor PCA with the same colleagues, which is in Annals of Probability, will appear this year. And this is done, in fact, for a more general class of model than Tensor PCA. Okay, and so what are the lessons we learn there? There we prove that Langevin dynamics and gradient flow started from a random initialization, correlate with a spike if the signal-to-noise ratio, as I mentioned last time, or equivalently the amount of data, is large enough. And the threshold, which is the amount of data is this, is the same as in the AMP. Okay. And in this case, when the amount of data is very large, what happens, so I told you the critical points, the maximum likelihood is in at a latitude, which is, I don't know, 70% of the North Pole. But when the signal-to-noise ratio increases, this thing goes to the North Pole. So here, the critical point is in a circle around the North Pole, which is extremely close to the North Pole, and where the topology there is trivial, or you only have a minimum. There's no complexity up there either, right? So complexity plays a role only if your amount of data is less than this. So complexity is just the study of bad news, right? That is when complexity is important when your system doesn't work, and then the system gets trouble. Here, both at the beginning, because the signal-to-noise ratio or the data is large enough, the push is strong enough to get away, and you have no time to visit the critical points, which I described in my former lectures, around the equator. And by the time you get up there are essentially no complexity left. Okay? So we also have a refutation below this threshold, but to be completely honest, our refutation is not starting from a random point, but something close to a random point. Just because we got tired of it, but it should be true. But there's still some room for a surprise. I would be extremely surprised if there was one, but there's still some room. The refutation here, we start from the Gibbs distribution at very high temperature. Okay? Okay, so the study of the online gradient descent for Tensor PCA is now done in a more general context, which includes Tensor PCA, the P plus K model, and the planted GLMs that I've described to you. So this is what I want to talk about today. OGD for GLMs, okay, or for this general class. Okay, so we consider again our empirical risk, loss, whatever, when the data are IID. And we define, of course, the online gradient descent. Here I'm on the sphere with step size delta. By this, you have at time t, x tilde t, you just take x at the time before, minus delta gradient. And then you divide by the norm to put it back on the sphere, right? Because this thing is not on the sphere, right? Of course, I could do this is not really online gradient descent on the sphere. I could also take a gradient on the sphere, follow this on the sphere. But here I do something which is probably easier to program, which is just take the usual gradient, follow the usual gradient, project back on the sphere. Okay? So, and of course I could, let's say, mu the distribution of the initial point. All right, so we assume here that, okay, you don't see that, sorry for that. Oh God, yeah. So let's call R the true population risk. We assume here that M is alpha n, I call alpha the ratio as before, and we assume that this population risk has a structure like this, where M is the correlation, the overlap, the latitude, whatever, with the spike, right? So, and we call capital K the first index where the coefficient of MK is non-zero. Note that this assumption is verified for both Tensor PCA and general GLMs. Right, for Tensor PCA, this true population risk is just the latitude to power P. So it's really something like that. And for general GLM, I told you it's true in general. And the VK here are just the squares of the coordinate of the activation function decomposed into the Hermite basis. Okay, so this is a fact. This is a very important fact that we noticed only recently, which shows that the two systems are in the same world. So the important here is the K, the capital K, the first index, that this is non-zero. Okay? Do you want to prove the fact that R is of that form for GLMs? Okay, no, cool. So let's look at the natural assumptions. So you need simple technical assumption on the initial measure. I won't go there, but let's say if you take a uniform measure on the sphere because you take something random, would satisfy them. And then you need some other assumptions about derivatives and smoothness bound on the derivatives of the sample error, which is, the loss for a given data minus so this is the mean of that, right? So this is just the fluctuation of it. Okay, so under natural assumptions on that, which are satisfied for Tensor PCA and for reasonable GLMs. For reasonable GLMs, we need an assumption about the actions, the activation function f to be in the Sobolev space of the from W14, if you know what that is, but forget that. So reasonable assumption on enough derivatives, in fact, and let's say 1 or 2, and 2, I think, and bounds on this derivative, integrability of those derivatives. Okay, then we can prove that that online gradient descent, which I just described, recovers the signal partially, as I mentioned in the Tensor PCA, in time t, which is of order m, the amount of data I have, because that's, when you do online, you don't repeat, so you just do you use your data. If you have the right choice of alpha, which is the amount of data, because remember alpha was m over n, and then delta, the step size, okay? So this is essentially the last thing to say, so which I mentioned quickly last time. So the simple models corresponds to k equal 1, so you have a coordinate 1. Again, in the p-spin model, it would correspond, or the tensor case, it would correspond to p equal 1. So think of what tensor PCA when p tensor PCA is when p equal 1. It's just linear regression for vectors, right? So that, I give you, there's a vector you don't know, and I give you a noisy version of it. Clearly, this cannot be a hard problem, right? So this is corresponds to k equal 1. Same thing for GLMs. Then in this case, you just need alpha larger than c, delta smaller than a constant. You have to play on those constants. All right? Then the critical models in k equal 2. So for instance, in the so again, if you look at tensor PCA, right? This would correspond to p equal 2 corresponds to matrices, right? That is, now I give you a matrix, and there is a matrix you don't know, let's say a rank 1 matrix, V star, and you have a noisy version of it, and you want to recover it. That's exactly the BBP transition, right? Because you're given a random matrix spiked by your rank 1 thing, right? So this is not a complex problem, okay? But still slightly more. So here, in this case in general, what we have is that we need alpha to diverge like log n square, and the time scales has to be chosen like 1 over log n square. So you need small time scale, step size, and largish alpha, right? Again, in those cases, when I say one needs, so that means Reza, Gesari, Okosh Jagannath, and I need to be able to make the proof. For the moment, we don't have, again, here, to be honest, we don't have a refutation. But that, for instance, it doesn't work if you have alpha equals a large constant, right? But it will come, I'm sure that it's not possible. But whether log n squared is the right thing, I don't know. Maybe it's log n squared divided by log n, or log to the power 3/2. I don't know. So that's the critical model. Then, of course, the hard model, where are they? Oh, they're coming. The hard model, when k is larger than 2, then you need alpha larger than this, which correspond to the threshold we had before. Because remember, alpha is m over n, so this means that m is larger than n to the k minus 2. In fact, this is slightly better than what I told you before for tensor PCA. What we have initially was that m had to be much larger than n to the p minus 2. Now here what we have is that it has to be larger than a constant times n to the p minus 2, so the threshold is sharp. And you need the step size to be really very small. Okay, and of course you can afford to do a very small step size because you have a lot of data. So this is what the so in all these cases you recover partially the signal. In fact, in this case here you recover, and in this case too you recover it almost perfectly, because it's the same situation than in the Tensor PCA. In the Tensor PCA, the place where your critical points, your maximum likelihood is a fraction of the North Pole, but when the signal-to-noise ratio diverges, this goes up. So here, because you have diverging things, it will, this is not proven, but I'm almost certain that it will be the case. That in these cases, you pay harder, but you get this. Well, by the way, of course, in the simple cases, you can also simply run your thing if you have a little more, if your alpha goes to infinity, not as a power of n or anything, or log n, of course also you will have perfect recovery. So here you have this result. So the proof, interestingly, so what we've discovered in the recent weeks or months is, so first we did this kind of thing for a version of online, but not gradient discrete algorithm, something stupid because we were used to that. What we have studied is Langevin and then gradient flow, which is of course continuous time. Then we studied the same kind, we had a version of online gradient flow. It really looks like online gradient flow or online gradient descent is the same thing, who cares, right? In fact, it's not the same thing. Mathematically, the thing for online gradient flow was much harder. And the reason is probably hidden in the fact that for online gradient descent here, we had this extra choice of the step size, right, which was kind of already done in the online gradient flow. So the proof of the online gradient flow is terrible, whereas the proof of this is short. It could fit in a decent paper. So that's the result. And as I said, we have no clue about what happens for this when you repeat. And so again, this covers, so let me say, this covers all the cases we've seen and all the natural cases we know on GLMs. If you take, so for the moment, of course, it's a planted thing, but if you take phase retrieval, it will be on the quadratic case, the critical case. If you take, regression, of course, it will be a simple case. If you take, so we've seen, when you have, so the real question for me at this point, I don't know, is to find really hard GLMs. That's, the pervert way of the mathematicians that try to see which one are really bad, fit in the third category exists for Tensor PCA, but which one, of the natural models studied in, so for that you have to decompose and compute the scale. We haven't yet done it. It would be interesting to see which of these natural estimation problems are hard. Now, of course, the next question is, of course, which of the problems of machine learning are hard? I am ready to say that this class will be essential. These three classes will classify all models. The next question is to know whether you can do that for 2 layers, 3 layers, many layers. What happens? And that I really don't know. I expect that many more of these models are hard, and navigating in the architecture of these to find doable model is much more complicated than. And I don't understand the geometry of these things at this point. But my message here is that there is a geometry. There is something to at least, of course, here, why is that doable and kind of simpler? It's precisely because I assumed that the data was Gaussian. Right? Because the data was Gaussian, I had this Hermite decomposition, which I could work well with, and Gaussian and the square that you have in the L2 loss go very well together. Hermite polynomial loves squares. So all that simplifies the matter enormously. If your data, as somebody asked recently, if your data is not Gaussian, of course you can do an orthonormal basis decomposition, but then your loss will be a strange object in this basis. So I'm not completely, this is one more level of difficulty to understand really general losses for general data, and even less for structured data, right? So this is the simplest, very simple losses, square loss for Gaussian, but general linear models, and then you have this classification. I still believe that this will be a classification valid for general models. But in order to know that, of course, we have to do numerical experiments. So there are numerical experiments on various real machine learning examples, which are reported in this work, comparing dynamics, even ICML, 2018, and Journal of Statistical Mechanics by Marco, Levent, Mario, Stefano, Chiara, Jan, Mathieu, and Giulio. And maybe there will be more on that this afternoon because two of the authors are all speaking. Okay, and this, of course, says being written by essentially physicists, and that the glassy picture is valid, of course, for machine learning, and so what we learn here should be true also for these general models. Okay, and I will stop here.